Greeting to everybody, and welcome to this new IAP colloquium. It's a pleasure to welcome today our colleague from Université Libre de Bruxelles, Geoffrey Compère. Geoffrey is currently Research Director of the Fonds National de la Recherche Scientifique at the Department of Physics of the Université Libre de Bruxelles. He prepared between 2003 and 2008 his PhD under the supervision of Glenn Barnish about symmetries and conservation laws in Lagrangian gauge theories, including application to gravitation, in particular through black holes. And apart from this initial expertise, he has been working on a variety of topics, such as ATS-CFT duality, as well as other bulk boundary dualities, black hole thermodynamics, or small particles in a black hole background, black holes endowed with a magnetic field, and so on, including also asymptotic symmetries with increasing connection to astronomy and astrophysics. And those works hold him wide recognition by the gravitation community. He's actually currently member of the Virgo and Einstein telescope collaboration, as well as the LISA consortium. Today we'll speak about gravitational waves produced by compact binary systems, and more precisely, hybrid post-Newtonian self-force, inspiral, and plunge waveforms. So the floor is yours, Geoffrey.
Thank you. Thank you, Franck and Guillaume and everybody for the invitation to be here. It's my pleasure. So I will talk to the entire community of IAP. So a large part of this talk will be discussing in broad terms gravitational waves, and I will have a couple of slides more on for the experts, but only a couple of slides, and I will try to be as general as possible. Please interrupt me during the talk to ask questions. You are very welcome. So this work, the technical work, is in collaboration with Loïc Honnet, Lorenzo Kuchler, and Adam Pound. So we are living in for the moment, in a detection era of gravitational wave. So last month, the 200th event was observed for detection of compact binary coalescences by the current collaboration of ground-based detectors, LIGO, Virgo, and CAGRA. So there are two detectors in the US, LIGO, Hanford, and Livingston, and Virgo in Pisa, Italy, and CAGRA in Japan. And with 200 events detected, and what is being seen are gravitational waves created by compact binary mergers. So here is a simulation from the University of Potsdam of an event with the best fit parameter of the event that was observed in 2023, and is a merger of a neutron star with a black hole. So I apologize, it's a bit, it's not totally smooth. Oh, it's smooth now, perfect. Well, nearly. So you can see a black hole, which is the smallest object here and the most compact, and a neutron star around it, which is depicted here as the largest object. And due to the gravitational wave emission, it's coalescing. And you see here that three different phases of the motion. The first one is the inspiral that takes place for the longest time. Then there is a merger, and then the final ring down at the very end. So those are the type of events that are being seen. So here are the current observing runs of the observatories. So it started 10 years ago, and there will be soon the celebration of the first detection that was in September 10 years ago. It occurred just before the science run, just during still the engineering phase. And you see here also the range of observations. You see we're around 100 megaparsecs of scale where these events can be observed. And we are currently in run 04, so in the fourth observing run. And you see that in the next observing run, there will be a significant upgrade of the detectors, and the range will be significantly increased. And so that will be the advanced plus LIGO, advanced plus Virgo. And now the Kagra, so the Japanese detector is joining the run 04 and will also join the next run. So here is a depiction as well of the range for the astrophysicists that are in the room or online. And you see the range with the various objects and clusters that are being under scrutiny of this detector with the different runs. So here is a depiction of the current 200 events. And you see on that plot, on the vertical axis, the solar masses, the mass in units of solar masses. And you see, for example, 2 black holes have been detected and produced another larger black hole. On that plot at the bottom, you see the neutron stars that have been detected through electromagnetic observations, and the black holes that have been indirectly observed through electromagnetic observations. And all the blue dots are black holes that have been observed with the gravitational wave detectors. And there are a couple of observations of neutron star mergers or neutron star black hole mergers. Sometimes it's not clear due to noise levels which one is which. And you see that this population is growing due to the increased observing runs. So this is only the beginning. Oh, it stopped showing the slides.
What's the significance being on the left or the right?
Oh, there's no significance. It's just for the beauty of the plot.
Okay.
That was done by Aaron Geller, and it was just for having a beautiful way to display all the events. So here are the 3 main missions that will be the 3rd generation gravitational wave detector. So the first one is the LISA mission, which is a mission in space. It has been adopted by the European Space Agency and consists of 3 floating masses, inertial masses that will go around an orbit around the sun at the back of the Earth, several million kilometers away, and that will just follow the orbit. And it will consist in 3 interferometers in a triangular shape that will probe lower frequencies because of the arm length is 2.5 million kilometers than the current ground-based detectors. On the ground, there will be 2 detectors that are currently under design at the Einstein telescope. The science case was released last month, a detailed science case of 800 pages long about what are the prospects of the science that can be made with this telescope. And in the US, there was this Cosmic Explorer with a timeline similar to the one of the Einstein telescope. So the current science range covers three main domains. The first one is about the nature of gravity in a strong field regime, and the compactness of the object makes the study of gravity really interesting in this strong range. So to test Einstein gravity and fundamental physics, there was a lot about population studies and also growth of black holes and galaxy formation, etc. And then the physics of dense matter, thanks to the collision of neutron stars, in particular the equation of state of neutron star, and then the properties of quantum chromodynamics and production of nucleons. So as in the electromagnetic spectrum, there is a gravitational wave spectrum. We can decompose the waves in frequencies, and the current interferometers to cover frequencies between 10 Hertz and 10 to the power 4 Hertz. And the main sources currently being observed are the compact binaries in our galaxy and beyond. For LISA, we will probe lower frequencies, and in particular, we see two new sources, the binary super black supermassive black holes, mergers, and also extreme mass ratio inspirals, so compact objects of stellar mass being captured by supermassive black holes of a million or billion times solar mass. So those are two qualitatively new sources that have never been seen before. So it's really an opportunity to see a universe in a different way. And in terms of, again, the range where this detector can observe. So for the moment, we are at the run 04, and we see redshifts up to 2. At run 05, there will be a redshift up to around 3. And the Einstein Telescope and Cosmic Explorer and LISA will see redshift up to 100, which will be before the birth of the first stars, which is around 100 million years after the Big Bang. So that's pretty incredible that we'll see the entire range. Here is in terms of populations. So the current advanced LIGO and advanced Virgo detectors see only, as I mentioned, around 200 events. At run 05, we'll go to advanced LIGO plus and Virgo plus, and we will see an exponentially growing number of objects. And for the Einstein Telescope and Cosmic Explorer, we just probe an entire range. As I mentioned, there are new sources, and the most important point to me as a person interested in fundamental physics is the signal-to-noise ratio will increase for individual events. So the loudest one so far has been around 50, and the expectation is that we will have events up to 2,000 for signal-to-noise ratio, which will allow really detailed probes of the physics around compact binary mergers. With the talk, so we have a huge challenge ahead to be able to derive these waveforms for all these events that we're going to observe. There are 3 main methods to derive waveforms. The first one is the post-Newtonian theory, and IAP is really the institute specialist in this post-Newtonian theory, so I'm not going to explain anything about it. You certainly all know about it. Then there is the gravitational self-force. So gravitational self-force applies for a mass ratio, which is here on the right, on the horizontal axis, for very low mass ratio, very asymmetric binaries. And then there is final numerical relativity, which applies for mass ratio that are not too high, otherwise there are too long separation of scales, and sufficient for 2 bodies sufficiently close to one another, because otherwise you need a lot of cycles, and there is accumulation of error during these cycles, so the mismatch is growing like the length squared of the time squared of the simulation. In fact, the previous plot showed that there is an intermediate zone which is without any modeling, but when you do a detailed study, as done in that paper, the small mass ratio expansion, in fact, is unreasonably effective at a comparable mass, and can reach for an equal mass case. So the waveform accuracy, yes?
If one were to project ourselves 10 years or 20 years ahead, how do you expect numerical relativity to progress?
Well, recently numerical relativity has been doing simulations for mass ratio 15, and trying to push to higher, but there is a wall of computational power to really go for higher symmetric mass ratios if it's numerical relativity alone. And in terms of number of cycles, there's also a wall, which is the growth with the square of the mismatch with the length. So you have to see the evolution of supercomputers. So there is the law of, the powers grow by 2 every 1.5 years, and so you can follow that law and then see where you can go with numerical relativity. I think all methods need to be improved. But let me go to 1 or 2 slides, and then they will be clearer. So the inaccuracy of waveform models may lead to errors in estimated source parameters, with errors about astrophysics, cosmology, or fundamental physics. So the inaccuracies arise either because we don't have enough all the physical effects, or because the modeling is insufficiently done. And the high sensitivity require that the waveforms get more accurate than compared to today, and they also need an increased range of parameter range for parameterizing the compact binary mergers. So here is a recent study from last month about one model, which is an effective one-body method model that compared the mismatches with, so this is the model that covers the entire parameter range of compact binary mergers. And they compare the mismatches with 1,700, if I recall, simulations. And to read that plot, here is the mismatch. So is the unfaithfulness of the waveform. So it's computed with a norm between the waveform computed from numerical relativity and the model. And there is a maximum because you have to align the waveform in time and in phase. So there are two parameters to tune. And then you try to align them the best to compute the best fit mismatch. And here are the not very faithful ones and the very faithful ones. And you see that on average, there was a faithfulness of 10 to the minus 3 currently for that model. Now, how is it going to go in the future? And this is where I can more precisely answer the question. So here is a study by Compère, 2019. So the well-accepted way that mismatch works with signal-to-noise ratio is there is a power law with a -2. So currently we have a signal-to-noise ratio around 50, and so we need an accuracy faithfulness of 10 minus 3. But with the Einstein telescope, for example, and then Einstein telescope combined with Cosmic Explorer, we'll go to signal-to-noise ratio that are above 1,000, and then we will need, with this power law, a mismatch which goes like 10 to the minus 5. And so there was a significant increase of mismatch that will be done. And then the applicability has to be collectively extended as well for the so-called intermediate mass ratio, where the masses ratio goes from 1 to 25 to 1 to 10 to the power 8. There's currently only one event that's been observed with a mass ratio, a high mass ratio, which is mass ratio 1 to 26. And for that event, there's been a study by the Virgo-LIGO collaboration that the systematic errors were comparable to the statistical uncertainties. So that points towards more modeling for the asymmetric mass ratios. And then we need to include various effects, eccentricity, spin, precession, tidal effects, environmental effects, and try to probe what can be said for other models than general relativity. Last but not least, and that's a tricky point, the waveform models have to be evaluated in milliseconds or close to milliseconds, because we need to do parameter estimation with these waveform models. And if you do a Bayesian interference, you will need to like 10 to the power 7 or a bit less or more, depending on what you want to study. But you need to evaluate this waveform many times to find the best fit parameters. That's the question, or?
I think you mean Bayesian inference.
Oh, inference. Interference, sorry, inference. Yeah, indeed, inference, of course. It was an interferometer for it, that was in my... So to be able to do that, you need a lot of waveform evaluation. So you need to have a model that is fast to evaluate. So all this to say, this is my motivation for developing these other waveform models. So let me now talk about the hybrid inspiral waveforms. Do you have general questions? So here now I'm going to concentrate on compact binaries, quasi-circular compact binaries, including primary spin. So as you know, there are 3 stages for the waveform, the inspiral, then there is a plunge. In fact, I like to call it transition to plunge because it occurs around the turning point, which is a real turning point, critical point of the dynamics. And then there is a final plunge. There is a framework to assemble composite solutions from each of these regimes in self-force theory. And in this talk today, I will discuss separately the inspiral and the plunge, but not about how you assemble them together. So the main motivation for this work is the recent results from this group that's produced the first self-force-based waveform for the vanilla case of a quasi-circular inspiral, so non-spinning objects. This model reproduces very well compared to numerical simulations the entire inspiral. And you see here the dephasing occurs at very late stages, very close to the plunge. And you see it compared with so-called adiabatic model where we only have the leading order set force. And that's start to be unfaithful for long inspirals. And then compared to a post-Newtonian only model. So these one post-adiabatic models have been successful for this particular simple case. So now we would like to see how we can extend this model to include also primary spin. So the self-force data is not available, but we have post-Newtonian data. So let's try to assemble the two together. So here is one technical slide, and I apologize, bear with me, but I need to just define my conventions for the experts. So we are looking at a waveform, and so I will define the total mass as the sum of the two masses, and the symmetric mass ratio as this quantity. Now we're going to use the numerical relativity convention. We will normalize the waveform with the total mass which is evolving in time, and then a real amplitude, and then the phase, which captures the entire complexity of the entire phase of the waveform, and as labeled LM, depending on the mode. Now, starting from the 2-2 mode, we can define the observable frequency. So normalize again with the total mass. And then we define the parameter X, which is the main parameter I'm going to use in the talk, from the observable frequency of the 2-2 mode. So the post, yes?
You are including black hole absorption for the...
Yes.
This is why
yes.
you assume time dependence.
Yes, indeed. So in this work, we don't assume that the secondary mass will change. We assume that secondary mass is fixed, but the primary mass will evolve in time due to the absorption of gravitational waves through the horizon.
But it's a very high order effect in the post-Newtonian.
Yeah, indeed. But it's more and more relevant when we get closer to the plunge. So we will include the effect. So then the self-force convention usually uses as a phase the orbital phase of the secondary body, because it makes an asymmetry, explicit asymmetry, and consider the secondary body as a small body orbiting the large body. So we are not going to use that convention, but there is a way to relate the two, and I'm not going to explain the details, but there is a way to change from the basic parameter of self-force theory and the one of the numerical relativity with a shift. That shift is adiabatic order, so it's first order in self-force, and it's a 4-PN effect in the post-Newtonian expansion. And there is a way to numerically obtain it using the 0-PA self-force approach. Okay, so now I define my convention. So what we need to look at the evolution of the phase of the 2-2 waveform, and we need to look at the phase of frequency, the evolution of the frequency now with the spin and the mass ratio, symmetric mass ratio. So we need evolution equations for these quantities to be able to deduce the waveform. And so the evolution equations are that form. The first one is easy, and so it's just the definition of the frequency. And now we need to compute the forcing terms. So the forcing terms, how are we going to deduce them? We will deduce them.
The mass ratio depends on time also.
Yes, the mass ratio also depends on time. Yes, indeed, because we start with initial time where, and then there is a change of masses, so it evolves in time. So, so I'm going to write down the evolution also of the symmetric mass ratio. So the total mass also depends on time, but there's a relationship between total mass evolution and mass ratio evolution, because we are assuming that the secondary mass, the smaller mass, is not evolving. So there is a simple relation between them. One mass that is evolving here. So what we are going to use is the fact that the energy is the total mass plus the binding energy. And the binding energy, we're assuming a function of the four dynamical parameters. And then we are assuming the flux balance law. So the fact that the flux of gravitational wave at infinity is minus the change of total energy of the system. And then we use also the fact that this is what Luke was saying, the change of the mass of the primary body is actually given by the absorption of gravitational waves. So this is the flux through the horizon of the black hole, and that gives you the evolution of the mass. And then the last relation we can use is the first law of binary point particle mechanics, which is a first law for binaries, and it relates the flux of angular momentum through the horizon with the flux of energy through the horizon. So when you play with these equations, and just with the definition of angular momentum and the spin parameter, and these look like ugly formula, but I just want to show that you can compute the formula. So you can write these flux, these laws as these forcing terms in terms of now these three quantities, which are the binding energy, the flux at infinity, and the flux at the horizon. So there is a finite expression, and what we now need to know is these two fluxes and binding energy. Yes.
Something which is not clear to me is that what do you define for the total mass or the mass of the black hole? This is the irreducible mass or the total mass? Because since you have spins, the total mass should contain some spin effects as well. Yes. Or is it defined as the irreducible mass?
So it's not the irreducible mass, which would be related to the area. Yes. So it is really the ADM mass.
The M total depends on your parameter chi.
Yes.
As well.
It depends. Well, it depends on time. There is a time evolution of it.
Yeah, and if in your absorption, the parameter M should depend also on your spin parameter chi.
So in the it depends on how. Yeah. So we are going to define it starting from the self-force approach, where in the self-force approach, the total mass would be the bare mass of the primary, which is time independent. It's the fixed background plus an evolution, and the evolution is due only due to the absorption by F. So it's totally defined independently of the spin. So with this definition, this adiabatic definition of the mass is independent of the spin. Yeah. So now we have to hybridize these three quantities. So we have to read off what are these three quantities defined, how they are defined in post-Newtonian theory, and how they are defined in self-force theory. So to start to comparing these two definitions, we have to align to define that at some initial time we have the fixed masses of the self-force theories, which is a fixed background. So and we choose it to be the initial time, the start of the inspiral. In fact, at the order where we are considering, the difference between M and MT does not appear in many expressions. It only appears in fact, the binding energy. And there we have to be careful. But then we have to take into account the fluxes at the horizon. But the main baseline is that we can choose common dimensionless expansion parameter and one mass scale, which is the total mass. And we can rewrite the two expressions in the same language.
Can you say very qualitatively what is self-force theory?
So self-force theory, yeah. So when you look at an asymmetric mass ratio case, so you imagine that you have a small black hole or compact object orbiting a very large black hole. At leading order in the mass ratio, the motion would be a geodesic. But then there would be a small effect because there is gravitational wave emission. So at leading order in a mass ratio, there would be a flux of energy and angular momentum. And then it will actually obey not the geodesic equation, but the forced equation with an acceleration, which is the so-called self-force. So it's a force of radiation reaction from the emission of gravitational waves. And so that can be computed from the metric perturbation due to the presence of the particle. So you solve Einstein's equation sourced by a stress energy tensor of the particle. And you couple those Einstein's equations sourced by the particle with the motion of the particle. That is on the left-hand side, a geodesic equation, and on the right-hand side is the force due to the metric. So this is a coupled system. You have to solve that system to solve your at the same time your motion and your gravitational wave emission. So that's what in self-force theory you do. You solve this coupled system. So now, and this is something.
And the small parameter is the fact that there's a small amount of energy being radiated, or
Mass ratio.
Mass ratio is proportional to the mass ratio, and we assume mass ratio is small. Okay. So now, we have two different expansions for the same three quantities. So we have binding energy and two fluxes, and we want to have a single formula for it. And so the first post-Newtonian type formula has this form in terms of this variable. So it's a double expansion in the x, which is related to the post-Newtonian parameter, to some corrections, and then the spin. And so you recognize the non-spinning term when there's no spin. Then there is spin orbit, spin, and increasingly spin couplings. And then the post-Newtonian expansion still contains some log term, but everything depends on the mass ratio. Now in the self-force expansion, we do an expansion in the mass ratio. So now we have terms that are proportional to mass ratio, and now this function depends on x and on the spin. So if we have, since we have by first principle, we both expansions are correct. So they should exist a triple type series where we expand in all of them. And then we can define an hybrid function by summing up to a given truncation order the post-Newtonian terms and the self-force terms, and removing the doubly counted terms. So we remove all the terms that are counted twice. And so that's the hybrid approximation up to a given order of that function. So the only remaining question now is up to which order can we define these quantities? So in terms of self-force data, we take adiabatic data from the community. So Martin van der Ment gave us the data on a Chebyshev grid with some very good numerical accuracy. We can derive the binding energy from the date-valued redshift, which has been published, and the mode amplitudes from the Tukowski solver, and that one is we get it from the black hole perturbation toolkit, which is publicly available. And then we have to be careful to switch conventions between spheroidal and spherical basis, and there was a very nice work that did it in very good generality. For the post-Newtonian data, we are using various articles that derive all these post-Newtonian orders. I just want to mention, especially to look, there is one that we use that is not in the review, which is the spin-spin sector at 4pn. And in fact, when we did not use it, the retrograde results were not really good, and they significantly improved when we included them. So, we use those results additionally. For the
one can no longer make some minor updates of the review. So I have to wait for a major update in. So this is the problem to include correction, not correction, but addition like that, small additions.
I see.
Problematic.
Well, yeah, there is a nice endeavor also of David to try to put all the PN data in one repository, which I think is very worthwhile to do. So in terms of the energy flux at the horizon, it's a different community doing it. So the authors don't overlap with the previous authors. It's funny. And there is that result at 4pn that we used. And then for the binding energy, here the result that we used, again, with an extra 4pn correction in the spin-spin sector.
What you call data here is not observed on the sky, right?
No, it's post-Newtonian derivations, analytic. So it's data produced by analytic computation. Yes. Maybe it's a better word than data, but we like to use data because it's been, definite analytical expression produced by the post-Newtonian method. And then finally, amplitudes. Again, these are just for bookkeeping purposes, but these are the main references that we used. So at 3pn order, 3.5pn, we have all the amplitudes up to very high L modes. And for the 2 amplitude, there is this remarkable work, 4.5pn that we used. So I will not discuss frame alignment because you certainly don't want to hear. I just want to point it for further discussion with the experts. And here are the models that we are finally looking at. So we are for the comparison. So I will look at the pure PN model, the adiabatic set force model, and then the hybrid one, and compare the three. And then we can also, when there is no spin, we can compare the results with the one PA, the one that I mentioned at the beginning. There was the most complete model for cell force, and the effective one body methods, which has well-established waveform models. So where we can compare with respect to those. So now let's go for the results. So I'm not going here also to discuss waveform alignment because that's very technical, or which simulation we selected, so that we can discuss the focus on the general result. So the implementation was done by Loïc Honnet, my PhD student, and fortunately was able to do it, a beautiful implementation. And here are finally the results. So here is a comparison between a given numerical relativity waveform and then the hybrid, the zero PA, so purely cell force based waveform, and post-Newtonian waveform. And this is a mass ratio 1, and the spin, which is around, which is 90%. So this is the primary spin, and here there is a upper bound, you know, it's 90% of the bound. As we see, well, we have obviously an alignment at early times, but then in the very late times, the PN, which is the truncation up to the order we considered, starts to deviate, and the zero PA deviates way earlier, but then the hybrids can go all the way to very close to the merger. So it improves both methods.
I have a question. You keep mentioning the spin. So you're talking about the orbital spin between the two objects. The objects themselves are not spinning?
No, it's the object themselves. So it's the intrinsic spin of the primary body, of the most massive body.
So the other one doesn't spin?
Yes.
Okay.
Yeah, so yeah.
And why do you assume that the other one doesn't spin?
It's because this requires a technical advancement in the formulation, and this is in progress, but it's not completed yet. So we need to add more sophistication to the model to include the secondary spin. So now again the mismatches. So the mismatch is based on an inner product between the waveforms. And now let me give one detail about the inner product. So this is the standard formula, and we do a Fourier transform of the waveform. And we go in the Fourier domain. We need what is called the power spectral density of the detector. And at this point, we are using the advanced Virgo plus power spectral density for the run 05. And we will truncate this for this mismatch computation at the ISCO frequency because our model is for the inspiral only. So we will only truncate up to the ISCO frequency. And for the lower bound, we select a batch of numerical simulation, and we go for the lowest possible frequency consistent with numerical error in that batch. And here are the results for the mismatches. So here's for a spin of 0.5, and for total mass around 50 solar masses. And we see for 0 PN, they have a mismatch of order 10 minus 5 for this case. We can estimate the error of the numerical simulation because we have we can look at lower resolution of numerical simulation and compare it with the highest resolution, and that gives you an estimate of the resolution. And you see that the hybrid and EOB mismatches are comparable for that case. So that's very encouraging. I will skip the details about energy fluxes and waveform dephasing due to the lack of time. And I will just show you here the conclusion of this study. So we have now this hybrid quasi-circular inspiral model with primary spin, and I merge assembles post-Newtonian cell force data, and that has better faithfulness than each model taken separately. And yes, comparable mismatches with SEOB models in the overlap range of validity. So we need to, of course, consider extension with secondary spin, indeed, precession or eccentricity. So we have that requires a lot of work still to be done, and extend, of course, inspiral to the plunge.
The small arrow to take it out.
It's well.
Yeah. Bottom left corner.
Yes.
There's a small arrow.
Yeah. Here, this one. This one.
This one.
Yes. Perfect.
That's better.
So maybe in the 5 last minutes, I would like to discuss slightly the plunge as well. I don't know if you have a question about this hybrid model.
I have a question. Numerical relativity could do the two-spin problem, right? I assume if you were to match your post-Newtonian or self-force model to a numerical simulation which has the secondary spin, how will that impact what are the errors?
Oh, yeah, really tremendous errors. So this is just it is not a good model. So the effective one-body methods are it's a well-developed framework that included already a long time ago the secondary spin, and these models are way more developed than this one. This one is a totally new model because based on set force and on its hybridization, and it cannot reproduce the accuracy that effective one methods are currently having for those cases. So this one is limited in scope. But the advantage of this hybrid model is that it extends a priori to intermediate mass ratios, because the effective one-body models calibrate certain parameters to numerical relativity. And here there's no calibration at all with numerical relativity. It's first principle only, in the sense there's only post-Newtonian and set force data that are being used to build that model. So now a word about the plunge. So here I will limit even the scope further. I will look only at the quasi-circular non-spinning compact binaries, and the ones based on set force. This is the state of the art, which is not that high, but we are planning to extend it. But at least we have to build a framework to be able to add all the effects. So here's the baseline case. So now I'm going to look at the final plunge here. And one key idea is the innermost stable circular orbit. So when you have a small body orbiting a large body, it has it evolves around a nearly circular orbit with a fixed radius, which lies at the bottom of your potential due to the main black hole. But then when it loses angular momentum, when you have your small body loses orbital angular momentum, the shape of the potential will change, and then at critical value, the potential will be such that there is no stable radial orbit anymore, and we start the plunge, and your body will go inwards. So in the first approximation, in this small mass ratio approximation expansion, you will want to look for the plunge at the orbit that starts exactly at the value of the innermost stable circular orbit for the energy angular momentum, and then plunge into the black hole. And that orbit is very special because it starts with a double root, at the ISCO. So a triple root, sorry, at the ISCO. So it starts at time going to minus infinity around the ISCO, and then it plunges, and then it reaches at time going to plus infinity the horizon. So this work has been, these waveforms have been derived many times in the literature, repeatedly, and so we are refining these results, and we did on the framework for further extensions. And so what we do, here is a Carter-Penrose diagram of the setting. So here's a plunging geodesic, and we are going to compute the waves emitted from this geodesic. So we saw the Reggie-Wheeler-Zerili equations in frequency domain. And then we perform a discrete Fourier transform, and we derive the time domain waveform. Now, the framework we are developing is already developed for post-geodesic order to go one order further than what has been done before, but we did not implement it yet. So here I'm going to show you the implementation of geodesic order and the comparison with numerical relativity. So here again, numerical relativity simulations. Here is the one with a mass ratio 15 and with a small residual intrinsic angular momentum of the spin of the final body. So for the moment, we are not doing a spin effects, but you see that if we have a simulation with low final spin, we capture well the peak of the waveform and the final ring down. Now, if we increase the mass ratio, more equal, we go for more equal mass ratio, we start with some more unfaithfulness. And if the final spin grows, then we have even more unfaithfulness because we are not modeling yet the spin. And then one final comment. We have really solved that problem. We have to solve a two-dimensional integral, and that is very computationally heavy. And that's the main roadblock of this computation. But fortunately, there is a highly oscillatory phase in that integral, so we can use stationary phase approximation. And then there's another trick called the quasi-normal mode approximation, where instead of integrating with this discrete Fourier transform on the real axis, we can deform the real axis into the complex plane, and then we reach complex, individual poles that are called quasi-normal modes, an arc, which includes all the time transient effects, and then a branch cut that allows to compute a very late stage of the signal. And so we can approximate that by just the poles. So it's called a quasi-normal mode approximation. And here is the result of how these approximations compare with one another. It's instructive to look at it. So the stationary phase fails to capture the leading peak. It stops just the peak before the leading peak. And the quasi-normal mode fails also to capture the leading peak. We have the one just after the leading peak. So the two approximations are complementary, but they don't cover the entire time range, and we are bound to solve the big problem because otherwise we just cannot obtain the signal. And here is the convergence plot of when you include more and more quasi-normal modes, and you see that when you choose 1, 2, and 3, etc., you just cannot reach to the peak. Okay, so that's the conclusion. So we are developing this framework for the plunge waveforms, and we are aiming to match it to the transition to plunge waveforms. But we implemented the model for the moment at leading order and compare it to numerical relativity and find good agreement, but just now for the case of small mass ratio and weak residual spin. And we need to solve this two-dimensional problem, it seems, because we cannot use approximations. So that was my main message for today. So thank you for your attention. Sorry for the technical problem of the presentation.
Thanks a lot. So we have time for more questions, if you have in the audience. Luc, okay.
So in your model, you use the innermost stable circular orbit, the ISCO. So I presume that you take the ISCO of a Kerr black hole, including the spin, the spin corrections and the spin contribution to the definition of the ISCO. But you are but you don't include the corrections to the ISCO due to the finite mass ratio between the two.
Indeed. So for the plunge part, the spin part is in development. We do even more basic. We don't even put the primary spin at the moment. Okay. But because we solve really regular equation, we need to upgrade it to solving the Tukowski problem and by including. But that framework is in development. But indeed we are the correction to the ISCO will appear at the one post-geodesic order, and so we have a framework that includes these effects, but we cannot yet implement it because we are lacking self-force data.
Well, it is known, I think, that in the two frameworks that you are using, post-Newtonian and self-force, you can improve the definition of the ISCO. In the self-force, the deviation of the ISCO due to the finite mass ratio has been computed numerically. at first order in the mass ratio. And in the post-Newtonian approximation, you can also define the notion of innermost circular orbit, innermost stable circular orbit.
Yeah, so definitely we should look at how to include these results to improve the computation. I agree.
Okay, more questions? Yes?
Yes, so thank you for the talk. So I just have a general question because do you plan to, I mean, I understand it's limited progress, but do you plan to include this type of waveforms in the analysis of LVK, of asymmetric LVK events?
So at the moment we are developing a model with the secondary spin as well. And we hope it will be interesting enough for the LVK collaboration, but yeah, we don't know.
More questions? Yes?
For data analysis, you are aiming for 10 million evaluations typically of these models. Did I get that correctly? Can you say again how expensive is it to get the numerical relativity solution, and how expensive is it for one evaluation?
So I think, if I'm not mistaken, if you want to do a full numerical relativity simulation of mass ratio Q equals 15, which is high mass ratio, and you need to have enough cycles to be interesting in the LVK band. Maybe around 20, at least 20 cycles, I would say. I think it's of the order of months on supercomputers to obtain one simulation. So at this moment, they obtained around 3,000 simulations. That's the order of magnitude that they have. That's accumulation, all simulations they've done. It's around 3,000.
And in comparison, one evaluation of one of your models.
So this model here, the vanilla model of 1PA, which is this one, has been published. Sorry, I will go back to that reference. So here, this model has been implemented in a very efficient way by Wardell, Warburton, and the collaborators, and it evaluates in 1 millisecond. So that one has been implemented in the Few package, and it uses hardware acceleration. It can run on graphical cards, so it's extremely fast.
Okay. Yes?
The fact that up to now secondary spin had not been included in the model, has this biased what we were able to detect, or it didn't matter because...
So this model is not being used for data analysis, for current data analysis. So this is really a theoretical work for the moment, and it was not used yet for parameter estimation studies. So, but there are models with secondary spin that are being used for parameter estimation studies. Surrogate models and effective one-body models that are various models inspired from all these frameworks.
So out of the 200 events that have been detected, how many were showing strong sign of spinning in either the main or the secondary body?
So basically all of them. So it's very hard to have an exact estimation of the primary secondary spin because it's a higher order. It's the most because the waveforms are mainly dictated by the so-called chirp mass, which is the specific combination of the two masses, and then the spins appear at lower order in the post-Newtonian approximation, and they appear at lower order also in the modeling. So there are very long, very large error bars for spins, for primary and secondary spins, but a priori there is a kind of bound that or expectation from numerical relativity that you reach really high spins, like around 60% when you have mergers, simply because when you are the ISCO and your orbital angular momentum at ISCO then will be absorbed by the black hole and will be converted to an intrinsic spin.
That's the post-merger spin. What about the pre-merger spin?
And the pre-merger spins, as well. There are indications that they are the spin are important.
Yes.
I don't know at the level of, I mean, precision that your model is considering. My question is relevant, but I am not sure that you consider the deformation of the black hole itself, because when the black hole is, I mean, isolated alone, there is no deformation. But when you consider two black holes, when they are very close, there is deformation. Therefore, I don't know if it is can be detected with your formulation, your model, or not, and how much important it is, especially for the ring down, because this is all the I mean fundamental physics is really in that part.
Yes. So these effects are included perturbatively. So either in the post-Newtonian framework, it uses perturbatively in terms of the frequency. It's an expansion in x, this parameter, or they are included perturbatively in the self-force framework in the parameter of the mass ratio. So up to some extent, these effects are included, but there is truncation. And then we do a partial resummation in the sense, for example, for the asymmetric mass ratio expansion, we expand really in the secondary mass divided by the primary mass. But then it's more useful actually, once we have this result, to say that we re-expand these parameters in terms of the symmetric mass ratio, so that we restore the symmetry between the two bodies, and that produces a different truncation of the real result, but which is more accurate with respect to numerical relativity situations. In that sense, we try to restore the symmetry by choosing how to truncate this, because we can never compute things exactly. We always have we can only compute up to a certain order.
Okay, so I think it's time to stop. So we can thank our speaker again. Right.